Welcome back. Right, so moving swiftly along, we have now arrived to our final example for sketching cubic functions. Right, so in this example, we are asked to sketch the function of y is equals to minus x cubed minus x squared plus 8x plus 12. Right, like usual, we begin by simply just analyzing our problem. Okay, we see that we have our mother function x cubed, right? We also see that this time we have a negative sign in front of that x cubed, so we do expect a reflection about the y-axis, right? But we also see that our mother function is not alone. It does have a lot of other parameters added onto it, so its shape is not going to be the same. These parameters, minus x squared plus 8x plus 12, are going to change the normal shape of the mother function. So once we've done that, we can then go straight into sketching our function. Right? We know that the first thing we always do is to find our y-intercept. Okay, when we do that in this above equation over here, right, we are going to have 0, 0, 0, and we'll end up with this 12 over here, leaving us with a y-intercept at 0, 12. And we know that for our x-intercept, we are eventually going to set y equal to 0, right? But in this case, because we're going to have to apply the factor theorem, let's make life easy for ourselves and move into functional notation, right? So let's say let y equal f of x. Once we have that, we now need to find a particular x value, right, that when we substitute into this formula gives us an output of 0, right? Once we've found that x value, we know that that is going to be our first factor. Okay, right, and remember I told you that one tip that I use to make an educated guess is I look at the value of d, right, and then you just try the factors of this value of d. Okay, so we know that 12, you can get 12 by 2 times 6. Okay, you can also get 12 with 4 times 3. Right, and what you then do is you always try the plus and the minus version of all of these values. So let us try first of all this positive 2. Okay, so substitute positive 2, and we see that our output is 16, right? So that means that x minus 2 is not a factor, right? So we go back in, right? Let's now try negative 2. Okay, and we see that negative 2 gives us an output of 0, right? Once we've received this outcome, we know that we've reached our first factor. Okay, so then therefore we can say that f of negative 2 is equals to 0. Therefore, x plus 2, right, is our first factor. Okay, now you have your first factor. Now you are ready to go into getting your quadratic factor, right? And remember I told you that getting your quadratic factor is the method you use is absolutely your choice. You can use polynomial long division, you can use synthetic division, or you can use inspection, right? For this example, let's use synthetic division. Okay, so you know that with synthetic division, you draw yourself the division sign, but it is upside down. Okay, and on the left hand side over here, you write down your first factor. In our case, it's minus 2, right? Then at the top over here, we're going to fill it in with all the coefficients of our original cubic function, right? So the coefficient of x cubed is minus 1, then we have minus 1 for the coefficient of x squared, then we have positive 8 for the coefficient of x, and lastly we have a constant term of 12. Okay. Then the first step is always to take the first coefficient and write it down as is. Okay, this is basically you setting up, okay, synthetic division. You haven't started synthetic division yet. Okay, now you are actually ready to start the process of synthetic division, and this is how it works. Okay, this first factor, right, comes in and multiplies whatever is at the bottom over here. Okay, so you're going to have minus 2 times minus 1. Okay, the result of that gets written underneath your next coefficient, right? So negative 2 times negative 1 is a positive 2, right? You can even write the positive there if it helps, right? Then once you have that, you then add going downwards like this, right? So you have positive 2 minus 1, that gives you a positive 1. Okay. Then you start all over again. Negative 2 times 1 is negative 2, right? 8 minus 2 is a positive 6, right? Then you start all over again. Negative 2 times 6, right, is going to give you a negative 12, right? And this is always the important step whereby when you add for your last column, right, that answer, right, has to be 0. Okay. And if you're wondering why is it so important for this answer to be 0, well, this answer being 0, right, confirms that whatever we have received over here is going to be the coefficients of our quadratic factor. So in other words, this x plus 2, right, divides into our original polynomial completely, such that the remainder, right, this is actually representing the remainder, right, such that the remainder is 0, right? Similar to when you were doing long division with normal numbers. Okay, just that now we're working with polynomials, right, which is functions. Okay, right, so as I said, these results at the bottom here become the coefficients of your quadratic factor, right? So then you are now going to be able to say that f of x, right, is equals to your first factor, which is x plus 2, times the quadratic factor, which is going to be minus x squared, right, plus x plus 6. Right. Now you are tasked with factorizing this quadratic factor over here, right? And you can see when you look at 6, you can work with 2 and 3, right? You can have 3 and lose 2, and you'll still have 1. Okay, so f of x can then be further factorized as x plus 2, right? And then we're going to need a negative x and a positive x, right? Let's write down a positive 2 over here, because that negative x times this positive 2 will give us a negative 2, right? So negative 2 plus 3 is a positive 1, okay? Then lastly, positive 3 times positive 2, we know will give us 6. Okay, so there we go. We have now factorized our quadratic factor, right? Now we go back to this instruction over here, because remember what we are doing is trying to find our x-intercepts. So we are now going to go ahead and set y, right, equal to 0, right? So when we set y equal to 0, okay, we are going to have 0 is equals to, now notice what has happened over here. We have 2 of the same factors. Okay, we've got this bracket of x plus 2, right, which has been repeated, right? And when this happens, right, it means that this x-intercept, right, this value of minus 2, right, is not going to be an x-intercept alone, right? It's actually going to act as a stationary point as well, right? So that means that we need to note that at x is equals to -2, right, our graph is tangential to the x-axis. In other words, when it gets to x is equals to -2, instead of crossing, it's going to bounce, right? And we just need to keep that in mind, right? So what I'm going to do is I'm going to write these brackets next to each other so that I don't forget. Yes, I'm going to write x plus 2, right, just so that I remember that I have a factor that is repeated, right? Then I have minus x plus 3. Setting each of these brackets equals to 0 will then give us our x-intercepts, right? The first one is going to be, we're only going to have 2 this time. It's going to be x is equals to -2 and x is equals to positive 3. Okay, so then we can jot that down in coordinate form. We have -2, 0, right? And you can put a little asterisk there, just to remind yourself that this one is special, okay? And we also have an x-intercept at 3, 0. Right, there we go. Right, now that we're done with our intercepts with the axis, we can now be concerned with our stationary point. Okay, and we know that for the stationary point, okay, we need to set f prime of x, right, equal to 0, right? I'm going to put back that instruction of let y equal f of x up at the top over here. Okay, so that will then allow me to say that f prime of x, right, is going to be equals to minus 3x squared minus 2x plus 8. Remember, we're just simply applying the power rule, right, to our original cubic function. Okay, and we know that that derivative is a quadratic, right? Then we need to set this equal to 0, right? So 0 is equals to minus 3x squared minus 2x plus 8. I don't really feel like factorizing this, so let's use our quadratic formula. Okay, so the quadratic formula will tell us that x is equals to minus b, which is minus 2, okay, plus or minus the square root of b squared minus 4 times a times c divided by 2 times a. We get a x value of minus 2, which we already know about actually, right? And when we go for the other sign of negative, okay, we get 4 over 3, right? So 4 over 3 is 1,3 recurring, right? Okay, so we now know that our x values at our stationary points, the first one is at x is equals to -2 and at x is equals to 4 over 3. Okay, right, so now we need the corresponding y value, so we need the f of -2, right? Well, we know what the f of -2 is, that's 0. Okay, then we're just going to need the f of 4 over 3. Okay, we get that the f of 4 over 3 is approximately, I'm going to write it to 3 decimal places, 18.519. Okay, so 18.519. Okay, let me just jot down our coordinates. Okay, and for the point of inflection, we know that we need to set f double prime of x equal to 0, right? We have our f of x formula over here, right? So we are now able to take f double prime of x, right? So f double prime of x is going to be minus 6x minus 2, okay? Setting this equal to 0 will give us 0 is equals to minus 6x minus 2. So then positive 2 is equals to minus 6x. 2 over 6 the negative is going to be equal to x. Right, so this is the x coordinate at our point of inflection. Right, so now we need the corresponding y value. So the f of negative, this is 1 over 3. Okay, this is equivalent to 1 over 3. Okay. Okay, and we get a corresponding y value of 9.259. Okay, so 259. Okay, so 9.259 as our corresponding y value. Okay, so for our intervals of increase and decrease, we just draw ourselves a derivative number line and you put f prime next to it, just to remind yourself that the test values, right, on this number line must be substituted into your f prime formula. Okay, right, so what are your critical points on this number line? Well, the critical points are the x values of your stationary points. Okay, and we know that we have a stationary point at -2, right, and we also have a stationary point at 1,3 recurring, right? And then we just need to get ourselves test values within each interval. Okay, so for the open interval from -infinity to -2, right, we can choose a test value of say -16, right? Why not? And for the open interval between -2 and 1,3 recurring, right, let's choose a test value of 0. That's a nice test value. Okay. And lastly, the open interval from 1.3 recurring to positive infinity. Okay. Maybe let's choose a test value of 20. Okay, so as you can see, I've now inserted our f prime formula into the calculator, right? And we are then going to substitute these chosen test values into the f prime formula, right? And that is going to give us the value of the derivative function, right? Now remember that the value of the derivative function, okay, is the gradient of the curve at that point, but it's also the gradient of the tangent line at that point. In other words, I'm evaluating the gradient of the tangent line at -16, right? And if the gradient of that tangent line, okay, is positive, that is telling me that for that interval, our f of x formula, okay, so our cubic function is increasing for that interval, right? If f prime is negative, then we know that our original cubic function is decreasing in that interval, right? What we're doing here is also called the post-derivative test, right? And this also helps us when we go into optimization, right? It's going to help us to identify whether or not a critical value that we obtain is actually a maximum or a minimum point, right? And we will see that in upcoming videos, right? So we need to test -16. Okay, and we get a negative value, right? I'm going to test all of them. So I know I have negative for the first interval. Then when we test 0, okay, we get a positive. And oops, when we test 20, we get a negative, right? So we're going from negative, positive, negative, right? So this is the value of the derivative function. It's also the gradient of the tangent lines along this f of x function, right? But if you want to interpret it even further, it's telling you that for this interval, right, f of x is decreasing, right? And then you're going to have a tangent line at -2, which is your stationary point, that's going to have a gradient of 0, right? And then for in between the stationary points, your f of x function is increasing, right? At the stationary point of 1.3 recurring, you're going to have a horizontal tangent line, okay? And lastly, for the last interval, okay, your f of x function is decreasing, Okay, and there you go. You now have the shape of your cubic function. Okay, so in this case, our shape is going to be go down first, then up, then down. And this shape of down first and then up, okay, this corresponds to a less than 0, right? And when we look at our original function, we see that the coefficient on x cubed is a -1. And yes, in fact, that is less than 0, right? Okay, we need to remember, okay, that this specific minimum right here at -2, right, we are not going to cross, right? So remember, it's doubling up as this x-intercept, okay? We're not going to cross, right, the graph at that x-intercept, but rather we're going to bounce like this. Okay, so we're going to have a stationary point. So here we go, we have our coordinate axis on screen, right? Now we know that from the shape, we need to go down and bounce, and then we need to go up, right? And this maximum is at 1.3 recurring, right? And the corresponding y value there is 18, all right? And we need a y-intercept at 12, okay? So we're going to go down, bounce, come up, peak, come back down. Okay. Right. Then we can label this. In this case, yeah, you can label it F, it's fine. Alright. Just put our X back there. Right. So then we just need to populate, right? Remember this sketch with all of our accumulated coordinates, right? So the most important one is going to be this one over here at x is equals to -2, right? And make sure that you develop yourself a system that reminds you, okay, when certain coordinates are special, right? So in other words, like for me, what I do is I put stars next to it. So I know when I'm looking at this x coordinate of -2, 0, right, there's something special about it, and I remember that helps me to remember that, oh, okay, if it's an x-intercept and a stationary point, right, I'm not going to go through the graph at x is equals to -2, but rather I'm going to bounce. Okay, then we know that this x-intercept is going to be this one over here of 3, 0. Okay, so this is 3, 0. Okay, we already covered this stationary point. We now need to just capture this stationary point, okay, which is our maximum over here. Okay, and that has coordinates of 1, 3 recurring, right, and a corresponding y value of 18, 519. Okay, so that's that stationary point. Okay, and then we have a point of inflection at -0.3 recurring, right? So we have -2 over here. This is 0, right? Oh, it's kind of squashed. Let's say halfway through here is -1, -0.3, something very close to y-axis. So let's choose to place it over here. We know that that y-intercept has a coordinate of 0, 12, right? And this point of inflection is, where am I going to write this? And the way that I'm going to label this point of inflection is because I don't really have space. Let's put an A on it. Okay, so put A, then I can write at the bottom here a equals minus 0,333, right, 9,259. Okay, and there we go. There is the sketch of our cubic function y is equals to minus x cubed minus x squared plus 8x plus 12. Okay, so I hope you were able to now see how everything comes together, okay, how you can move from a general formula of f of x is equals to a x cubed plus bx squared plus cx plus d, right, into any one of the following three sketches, right? The one here at the left representing when a is greater than 0, and all that you need to remember is that when your a value is greater than 0, it's telling you that you're coming in from the left hand side. You go up first, then you go down, then you go up, right? Connecting your points. Right? And if a is less than 0, it's telling you that you're starting from the left hand side. You come in and you go down first, then you go up, right? And you do that connecting all of your points, right? And in today's video, we saw that sometimes it happens that you are going to have two of the same factors, right? So in other words, the bracket x plus 2 repeated, right? And when that happens, okay, it means that the graph is basically going to bounce, right, at that x value, right? We say that it is tangential to the x-axis at that point, right? And then just key points is that for your stationary points, you set f prime equal to 0. For your point of inflection, you set f double prime of x equal to 0. And all of these actions give you the x coordinates at your stationary point and your x coordinate at your point of inflection respectively, right? Those x coordinates need to be then taken back into your given f of x formula to find the corresponding y values, okay? And when you are looking for your x-intercepts, right, we apply the factor and remainder theorem, right? And once we've received our first factor, then it is your choice to use either polynomial long division, synthetic division, or inspection to find the other factors, right? And then your derivative number line basically gives you your intervals of increase and decrease. In other words, it's also telling you, right, where you will have your maximum and where you have your minimum, okay? And on your derivative number line goes the x values of your stationary points, and we call these critical numbers, right? Then the test values are what give you the sign, okay, or the derivative function, okay, the value of the derivative function. Children, this brings us to the end of curve sketching. I hope that you've enjoyed it, and remember to practice, practice, practice.